Here's an example of finding the volume of a solid of revolution using the method of cylindrical shells. Let's find the volume of the solid generated by rotating the region bounded by y equals 4x minus x squared and y equals 3 about the y-axis. As always, we'll want to start by graphing the region. We want the region bounded by y equals 4x minus x squared and y equals 3. This parabola, if you factor it, you'll see that it's going to cross the x-axis at the origin, at 0, and at 4. So crosses here. And because the coefficient on the x-squared is negative, it's going to be a parabola that opens downward. So it should look something like this. Meanwhile, the line y equals 3 should go right across here. Crosses that parabola at 2 points, and the region is the region in here. In fact, we can find the points of intersection between these two curves by setting the two y's equal to each other. 3 equals 4x minus x squared. If you work this out and take all the steps, you'll find that x equals 1 or x equals 3. I'm not going to show this whole process because you know how to do this already. So we can see that our line crosses the parabola at x equals 1 and x equals 3. These are therefore going to be the bounds on our x. Next, we'll want to draw the solid of revolution that we get by rotating this region around our axis of rotation. Our axis of rotation, in this case, is the y-axis. So here is our axis of rotation right here. You can put a nice circular arrow there to show that you're rotating about the y-axis. And if we rotate this, we're going to end up with something that looks like this. And the three-dimensional shape that we get, I would describe it as perhaps a sort of bundt pan. You know, one of those cake pans that has a hole in the middle and sort of lumps on both sides. It's sort of, maybe you'd call it the top half of a donut. Our next step is to look at what happens if we rotate a typical Riemann rectangle about this region. Since x is our variable and y is a function of x, as usual, we'll want to draw a vertical-looking rectangle right in here. If your variable were y, you'd draw a horizontal rectangle with the height x being the height of the rectangle. Because our rectangle is actually parallel to the axis of rotation this time, when we rotate this rectangle about that axis, it's going to trace out a cylinder shape. A cylinder with some thickness, in other words, a cylindrical shell. That's more or less what it looks like. This is the cylindrical shell that's at position x. And again, the reason that we have a cylindrical shell this time and not a disc or washer is because our rectangle that we drew, which is vertical because it's at position x, x is our variable, y is the function, so it goes in the y direction. That rectangle is parallel to the axis of rotation. That's why it traces out a cylindrical shell. If you look at other rectangles that make this up, rectangles that are to the left of this one will make cylindrical shells that are smaller, that fit inside this cylindrical shell. Rectangles to the right of this one will make wider cylindrical shells that fit outside this. So you'll have a series of concentric cylinders, sort of like imagine a roll of paper towels. In fact, we could take one of those cylindrical shells and imagine slicing it open and unrolling it so that it forms a sort of rectangular shape. Like this, right? You could unroll it to make a nice flat rectangle with some thickness. It's not exactly a rectangle, of course, because the inner circumference on the inner surface of that cylindrical shell would technically be a little bit smaller than the outer circumference. But because we are assuming that our shell is very, very, very thin, we can get away with unrolling it and saying that it makes a nice rectangular prism. What are the dimensions of this? Well, the cylinder has a radius we'll call r and a height we'll call h. So our rectangular piece also has a height we'll call h, but the length of this, if you unroll it all the way, is the circumference of that cylinder, which is 2 pi times the radius. And of course, the thickness of this thing is dx. It's the width of the rectangle. So there, your dx is appearing naturally in the solution, just as it always does. So the volume of one cylindrical shell is going to be the length times the height times the width, which is going to be 2 pi r h times dx. And therefore, the volume of the whole solid is the integral of this expression. It's the integral of 2 pi r h dx from some bound to some bound. This is the general formula for the volume of a solid of revolution using the method of cylindrical shells. As long as you can find the radius of the xth cylinder and the height of the xth cylinder, you're all set. So let's work out the details in this particular case. What is the radius of one cylinder? The radius is always the distance from the axis of rotation, the center of that cylinder, to the position of that shell. Since our rectangle in our diagram is the xth rectangle, the rectangle that's at position x along the x-axis, and our axis of rotation is when the x is equal to 0, that radius is just going to be x. You could say x minus 0, which is just x. In fact, in the method of cylindrical shells, the radius will always be fairly simple. It will always be either x, or x minus a number, or a number minus x. What is the height of this particular cylinder? Well, it's just going to be the height of the rectangle that we use. It's going to be the top function minus the bottom function. In this case, our top function is that parabola. The y value is 4x minus x squared. And our bottom function is the line y equals 3, so we can say minus 3. And that is our height. So now we're ready to put this information together into the integral that solves this problem. We determined that the radius of one particular cylindrical shell is x, and the height of that shell is 4x minus x squared minus 3. The formula for our volume, we can pull the 2 pi to the outside and say 2 pi times the integral from some bound to some other bound of the radius times the height times dx. We just need to fill in these details. This is going to be 2 pi times the integral of x, which is the radius, times the height, which is 4x minus x squared minus 3. times dx. What are the bounds? We already determined when we drew our graph that the bounds on x are from 1 to 3. So this is the volume of our cylinder. I'm not going to take the time to actually evaluate this integral in this case, because this is a pretty straightforward integral that you know how to do. I would encourage you to practice this if you feel that you need more practice at solving integrals of polynomials. Now let's look at what changes if we try and rotate our region about a different axis of rotation. Let's now use the axis of rotation x equals 1. So now, instead of the axis being the y-axis, we're going to use this vertical line x equals 1. This is our new axis of rotation. What kind of solid do we get this time? Well, we're going to rotate this region around a closer axis. It's going to look more like this time. And it's going to be that sort of, bunt pan again. I would describe it that way, or the top half of a donut, but the top half of a donut whose hole has very nearly closed up. Now we can find our cylindrical shell again. We're still going to use a vertical rectangle because we still have y as a function of x. So the height of the rectangle is a function of its position, which is x. Because that rectangle is still vertical, it's still going to trace out a nice cylindrical shell when it gets rotated. Something like this. In fact, very little changes about our cylindrical shell. The height is still going to be the height of this rectangle, which has not changed. The height is still the top function minus the bottom, which is 4x minus x squared minus 3. That has not changed since the previous version. However, the radius has changed. The radius is now going to be smaller than it was. It's only the distance from the axis of rotation to the position of the rectangle. X on this x-axis represents the distance from the origin to the rectangle. That's x. The radius is only the distance from 1 to x. So it's going to be x minus 1. Our radius in the previous example was x. Now the radius is x minus 1. So we can put together our volume formula by saying that our volume equals 2 pi times the integral of RH, our R is x minus 1, you put that in parentheses, times our H, which is 4x minus x squared minus 3, times the thickness of the shell, which is dx, and our bounds are the same. The bounds still go from 1 to 3. This is our new volume formula. By changing the axis of rotation, in this case by shrinking our solid, because it has a smaller radius, the axis is closer to the region. The only thing that has changed about our formula is that our radius is now x minus 1 instead of x. And this integral you can solve just as easily as the previous one. Just do a bit of algebra to expand and multiply out this polynomial, and then you can just integrate the polynomial very easily. So I'm not going to walk you through those steps. You know how to do that. Finally, let's use the axis of rotation x equals 5. That's this line right here, this vertical line, x equals 5. We'll rotate about that line. And this time our region is going to wind up over here somewhere. And rotate it. This time you're going to end up with a very wide top half of a donut. So again, this time, we can look at what happens if we rotate our typical Riemann rectangle. Here's our rectangle, the rectangle at position X, and that will get rotated around and wind up over here somewhere. Again, it will trace out a cylindrical shell, and we can, again, find the radius and the height. And again, this time, the height still has not changed. The height is still the top function minus the bottom function. It's the height of the rectangle. It's going to be 4x minus x squared minus our lower function, which is 3. What is the radius this time? Well, the radius, as always, is the distance from that rectangle to the axis of rotation. It's the distance from here to here. This is the radius. In other words, the distance from x to 5. So that's going to be 5 minus x. Notice that the order of our subtraction has changed this time. In the previous example, the axis of rotation was 1, which was to the left of x. So we said x minus 1. This time, our axis of rotation is 5, which is to the right of x. So we'll say 5 minus x. You need to make sure that you are doing your subtraction in the correct order so that you get a positive result, because all of the x values that we are going to use for our integral are between 1 and 3. They're all less than 5, which means this radius is always positive. And again, we can put together our volume formula. That volume is always going to be 2 pi times the integral, same bounds as always, from 1 to 3, of our radius times our height. That is 5 minus x times our height, which is 4x minus x squared minus 3, times the thickness of one of those cylindrical shells, which is dx. And this is our formula for the volume. And again, for the third time, this is a fairly simple integral. Again, you can expand out this polynomial and then integrate it fairly easily. So I'm not going to show those steps because you know how to do that. This is the basic process for finding the volume of a solid of revolution using the method of cylindrical shells.